Nonparametric statistics are statistics that are not based on assumptions about population distributions. The chi-square test, for example, is considered a nonparametric test because the chi-square test does not involve assumptions about the population. A typical chi-square test starts with data like the data in this table and works by computing a test statistic that uses observed and expected counts of individuals in various categories. Since this process does not involve constraints on the population of counted individuals, the chi-square test can be used in situations where a corresponding parametric test may not apply. The most common nonparametric statistics are hypothesis tests. This section includes brief examples of a very simple hypothesis test called a sign test and another test called the Mann-Whitney U test. The sign test can be used, among other things, to compare the median of a population with a hypothesized value. For example, consider the measurements in this table, which shows 12 measurements of the flow rate of water in a stream, and using those measurements in a hypothesis test to decide if the flow rate is equal to the historical average. One way of doing this hypothesis test is with a t-test. The null hypothesis is that the flow rate is equal to the historical average of 14.0. This input enters the flow rates shown in the table, and this uses the t-test function to do the t-test and get a p-value, but the calculation also gives a warning message about possible non-normality of the data. Validity of the t-test depends on various conditions, one of which is that the population from which the sample is drawn is at least approximately normally distributed. A number line plot of the data shows several values well to the right of the rest of the data, indicating that, unlike the normal distribution, the population distribution may have a long tail to the right. The sign test is a nonparametric alternative to the t-test. For the sign test, it is appropriate to use the historical median rather than the historical mean as the hypothesized value, so that if the null hypothesis is true, the probability of a measured value being larger or smaller than the hypothesized value is 0.5. Here is the data table showing the sample of measured flow rates, the difference between each flow rate and the historical median, and the signs of those differences. The test statistic for the sign test is the numbers of positive and negative signs. The sampling distribution of that test statistic is a binomial distribution. Here's a plot of the binomial distribution for 12 trials and probability 0.5 for each trial. In this example, there are 3 negative signs and 9 positive signs, so the two-sided p-value is the area in the tails of this distribution below 3 and above 9, which can be computed using the cumulative density function CDF of the binomial distribution. If the conditions for validity of the t-test are satisfied, the t-test is almost always more sensitive than a sign test, which means that the t-test is less likely to give false negatives. The advantage of the sign test is that it can be used in situations where conditions for the validity of the t-test are not satisfied. These principles are quite general. Parametric tests tend to be more sensitive, but the conditions for validity of a parametric test are generally more restrictive. Another common nonparametric test is the Mann-Whitney U test, which can be used for testing whether two population distributions have roughly the same shape and location. For example, consider data for flow rate of water in a stream in 2 different years and doing a hypothesis test to determine if the two flow rates are the same. The hypothesis test could be done using a t-test, but as in the previous example, the t-test may not be reliable due to non-normality of the population of flow rates. The Mann-Whitney U test is done by sorting the two lists together, assigning a rank to each element, and adding up the ranks to get a rank sum for each list. The test statistic for the Mann-Whitney U test is traditionally denoted by the letter U and is the smaller of the two rank sums minus n times n plus 1 over 2, where n is the size of the sample. Calculation of the p-value is complicated by the fact that the sampling distribution of this test statistic is not a commonly tabulated distribution. The p-value is typically computed using various approximations. This input shows the p-value computed using the function Mann-Whitney test, which computes the test statistic and a p-value using one of those approximations. As with other nonparametric tests, the advantage of the Mann-Whitney test is that it does not depend on any conditions on the distributions of the populations from which the samples were drawn.